Hello, this is chemistry lesson 6.07, and we're going to do some practice problems today with molecular geometry and hybridization, and we're also going to get some extra practice drawing Lewis structures. So let's go ahead and get started. Let's start with, let's do SO4, so 4 oxygen, 1 sulfur with a -2 charge. We're going to learn in the next, so this is example problem number 1. We're going to learn in the next chapter that this is called sulfate. It's got a name and it has a charge, so it's a polyatomic. All right, for my structure, I'm going to put sulfur in the middle, surrounded by the oxygen. And now I need to figure out how many electrons I'm allowed to have. So I have got oxygen, I have got sulfur, I've got 4 of these, I've got 1 of these. When I look on my periodic table, I see that oxygen has 6 electrons, and I see that sulfur is the same. So this is going to add up to 30, but I have to do extra because I have a -2 charge. So I get a total of 32 electrons. I'm going to go ahead and apply these. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, this structure isn't going to be too tough. When I redraw this with bonds, it's going to look like this. Because it has a charge, I have to do brackets. The -2 outside. So now the question is, what is my hybridization and what is my geometry? Well, if I look at my central atom, I have 4 sigma bonds. So that tells me this is going to be sp3. And if you've memorized your geometries, or go ahead and look on your table, if we have 4 sigma bonds, this is going to be tetrahedral. And we'd see that these bond angles all have a 109 angle between them. And if I was going to draw this out in a 3D way, which you don't have to, but the actual geometry would look like this, drawn out. With brackets, and then so that's our way of representing that this bond's coming out of the paper and that bond's going in. All right, for these next 2 examples, why don't you pause the video and see if you can do them. Okay, so for example 2, let's do 1 oxygen and 2 hydrogen. Okay, go ahead and pause the video and take your best shot. All right, hopefully, welcome back. Hopefully you figured out that we're talking about water here. So this is H2O. So we're going to put oxygen in the middle and, oops, yeah, good enough. I'm going to put hydrogen on the outsides. So I need to know how many total valence electrons I'm allowed. And when we look at our periodic table, we see that oxygen has 6 and each hydrogen has 1. So I'm allowed a total of 8 valence electrons. So I go 2, 4, 6, 8. Remember, hydrogen only has to have 2 electrons to be satisfied. So this is actually good for hydrogen. And when I redraw this structure, I would have all right, so what is my hybridization and what is my geometry? Well, hybridization, I'm going to have 2 lone pairs, and I'm going to have 2 sigma bonds. So this has got to be sp3. So I have 4 hybridized orbitals. So when you have 4 hybridized orbitals, that means it's going to require all 3 of the p's and the s. Now, my geometry, when I look on my chart, I see that if I have the chart shows the lone pairs up here, shows the oxygen, and then it has these hydrogens. So it looks a little bit like that. When you look for the box that matches the two lone pairs and the two sigma bonds, and this geometry is bent. So water is a bent molecule. And this is why back in the last chapter when we talked about hydrogen bonding, because it's bent, it gives us a partial positive and a partial negative on each end. So um, that's why we get the properties that we do. So, all right, let's go ahead and go on to example 3. Example 3. We've got a boron and we've got 3 chloride. All right, go ahead and take, whoops, 1 boron and I've got 3 chloride. All right, go ahead and pause the video and take a crack at that and see how you do. All right, so welcome back. Let's go ahead and do a stick structure here. So I'm going to put my boron in the middle and I'm going to put my chlorides around here somehow. We're not quite sure how. Now we need to look at my allowable valence electrons. I've got boron and I've got chlorine. I've got 3 of those. I've got 1 of those. And each chloride has 7 for a total of 21 electrons. And boron has 3. So we're going to do a total of 24 electrons. Here we go. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Well, when we do my octet check, chloride has 2, 4, 6, 8. This has 2, 4, 6, 8. This has 2, 4, 6, 8. But boron only has 6, but that's okay because remember, boron is an octet exception. It does not have, it doesn't need 8 electrons to have a full valence. So when I redraw this, so, and I kind of drew it with the geometry that I know it's going to have. So what I have here around boron are 3 sigma bonds. So that's going to give me an sp2. I have 3 hybridized orbitals. So that's going to require an sp2 hybridization. And 3 sigma bonds around a central atom is going to be a trigonal planar. Trigonal planar. All right, since I have room, let's do one more example. Let's go with example 4. I've got 1 carbon and I've got 2 oxygen. All right, so my stick structure is going to be pretty simple. Let's go with orange. Carbon, oxygen, and oxygen. So carbon has 4, oxygen, I have 2 of those, so that's going to be 2 times 6 for 12. So I'm going to have a total of, whoops, check my mental math there, 16 allowable electrons. So I'm going to go ahead and apply those to 4, 6, 8, 10, 12, 14, 16. But when I do my octet check, oxygen is okay. This oxygen is okay, but this carbon only has 4. So what I'm going to have to do is I'm going to have to bring lone pairs down for double bonds. And I end up with carbon over here, whoops, with lone pairs. So let's check this Lewis structure. Total count 2, 4, 6, 8, 10, 12, 14, 16. Carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8. This is a good Lewis structure. Now, when I look at my, when I want to decide what I have for hybridization, around my central atom, which is here, I have 2 sigma bonds. Well, what about these other 2? Those are pi bonds. Those don't count. It's sigma bonds that determine that are in hybridized orbitals. So my hybridization here is going to be SP, and I have 180 degrees. The only choice I have here for geometry is linear. Okay, so hopefully that helps get you up to speed on determining orbital hybridization and molecular geometry. And that also wraps up this chapter. So thanks for watching and have a great day.